Hi, my name is Harrison Williams. I'm going to be presenting our work, Energy Adaptive Buffering for Efficient, Responsive, and Persistent Batteryless Systems. This work targets energy harvesting sensor systems, which are mobile and IoT scale devices that replace bulky, limited, and volatile batteries with energy harvesting circuits, which enable the systems around them to be built smaller, operate perpetually, and be deployed in environments where the volatility of batteries is unacceptable. Basic batteryless systems look something like the diagram on the right, where the batteries are placed with an energy harvesting circuit and a buffer capacitor to power the system. The energy harvester slowly charges the buffer capacitor up to some enable voltage, in this case 3.5 volts, at which point the system turns on and rapidly drains it in a short burst of operation down to some lower disable voltage, say 1.8 volts here. An important element of this system is that the capacitor, of course, is chosen at hardware design time. The size of the capacitor chosen is informed by system requirements, which can change throughout execution. Sometimes our system needs to rapidly charge up to an enable voltage to carry out relatively low power operations like sensor readings, which lends itself to a smaller capacitor. Other times, we're better off buffering a lot of energy to reduce software overhead from restarts or to enable high energy atomic operations like radio transmissions. In this case, we would prefer a larger capacitor. Because we can only have one capacitor in a typical system, the compromise that we use is that we take the minimum sized capacitor that will still enable the largest atomic operation to complete without additional input power from the energy harvester. Capacitor size introduces a system level trade space. Smaller capacitors charge more quickly but also discharge more quickly. They can't buffer a lot of energy for a single operation. Larger capacitors are the opposite. They take a long time to charge to the operational voltage, but once they are charged, they can sustain a long-running chunk of execution. We can say that systems with small capacitors have high reactivity because they enable with relatively low input energy, but they also have low persistence because once they start running, they can't run for very long because they don't have very much energy buffered. Large capacitors need a lot of energy to charge to the enable voltage, so they have low reactivity, but also have a long discharge time, which means that they have high persistence. Further complicating our trade space, a lot of the deployments where we expect energy harvesting systems to really hit their stride have input energy that looks something like this. They're highly volatile, with a lot of input energy contained in short-term power spikes that are well above the consumption of the system itself. If our capacitor is too small, this energy may need to be burnt off as heat to prevent hitting the overvoltage limit. So this means that we need capacity to capture these power spikes that we see in real-world systems, but without compromising system-level charge time. So to overcome the reactivity persistence trade space, the state-of-the-art introduces what I call here capacitor multiplexing, which enables the system to switch between different capacitors of different sizes throughout the program. On the right is our sense, compute, and transmit application, modified to use this capacitor multiplexing approach. When we need a smaller capacitor, we switch to the small capacitor to take our sensor readings. And we need to buffer a lot of energy for our radio transmission, we can switch to our large capacitor. Systems with capacitors multiplexed together can operate at different points in the charge time capacity trade space depending on their immediate needs in the application. They can also capture excess incoming energy in additional capacitors to reduce the chance that the system needs to burn off any incoming power as heat. Unfortunately, we demonstrate that this approach introduces a couple of design and performance level problems stemming from the concept of energy fragmentation across capacitors. Let's look at a simple toy example where we charge our small capacitor first and our large capacitor second across a couple of power traces. With a flat input power of 1/4 of a milliwatt over a trace of 50 seconds, we run exclusively off of our small capacitor with a sort of typical batteryless operating mode shown here on the bottom right, where we charge the small capacitor up to the upper voltage, we discharge it to the lower voltage, and we see an on time of 29 seconds. We never need to use the larger capacitor. However, if we concentrate all of our input energy in a short-term power spike in the beginning of the trace, we see the problem. The small capacitor rapidly charges to the enable voltage, and all incoming power is then redirected to the larger capacitor. Eventually, the power spike ends, and we run exclusively off the power or the energy in the small capacitor. Eventually, that capacitor discharges down to the disable voltage, and now we have energy fragmented across both capacitors, but both at voltages that are too low for us to run off of. So we've had the same energy input, but we only see an on time of 16 seconds, and unless we get more energy later, the energy on both capacitors will eventually be lost to leakage. Energy fragmentation also complicates design. If we refactor our sense compute transmit application to the event-driven model shown here on the right, the problem is apparent. It's not immediately clear which capacitor I should charge first, because I don't know which event is going to fire first. Every capacitor is associated with a different event in the program. If I charge one capacitor, assuming I'm going to execute that event next, I can't change my priorities. Energy is allocated to that task at harvest time rather than when I actually execute it. We can say that energy in this sort of system isn't fungible. Now we've gone over some of the limitations of the state of the art. We can formulate our problem statement. First, we see that there's this charge time capacity trade space that we would like to eliminate using a unified energy interface. We'd like to provide reactivity and capacity while also maintaining energy fungibility to simplify programming. We'd also like to do the above entirely without forcing the programmer to reason about incoming energy or future energy budgets. We need a system that expands and contracts capacitance according to stored energy. The most intuitive way to do this is to have a single common supply rail that I connect and disconnect capacitors from as needed. So we have a system like that here. We start with one small capacitor, and we can charge it up to some upper voltage, say 2.4 volts. We can expand capacitance by connecting a second capacitor to the supply rail. However, connecting an uncharged capacitor to the high voltage supply rail causes current to flow to equalize voltage between the charged and discharged capacitors. This causes resistive heating that dissipates our stored energy. If we double our capacitance this way, we lose half of the energy we had buffered to resistive heating during the current spike. So we pay a high price to increase capacitance with this system. To make matters worse, if we want to reduce capacitance to increase our system's reactivity, all we can do is disconnect capacitors. This means that any energy that we had on those capacitors is now unavailable to the system and will eventually be lost to leakage. To overcome this, we borrow a circuit from the world of power electronics known as a charge pump, with the actual implementation shown on the upper left and the equivalent circuit shown on the bottom left. In this configuration, with two capacitors of equal size, the equivalent capacitance seen on the supply rail is C over 2. This gives us high reactivity. With a small amount of energy, we can rapidly reach an enable voltage and begin operation. If we need to increase our capacitance, all we do is flip the double pole double throw switches into the opposite configuration. This produces the equivalent circuit on the bottom left. We've gone from equivalent capacitance of 1/2 C to 2 C. We've cut our voltage in half, but we haven't lost any energy doing it. So we've realized variable capacitance and voltage without energy loss. When we're discharging this system, or just to reduce capacitance to increase reactivity, all we need to do is flip the switches back into the opposite configuration, going from an equivalent capacitance of 2C to C over 2, doubling our voltage, which allows our system to continue extracting energy from the capacitors because they're at a voltage that the system can run at, again without dissipating any energy. So this increases energy extracted from the system. These charge pump circuits form the foundation of the system that we call React. We connect a number of capacitor banks to a common supply rail, where each capacitor bank is a charge pump with the architecture shown below, to achieve an arbitrarily high capacity without affecting charge time because no capacitor banks are initially connected to the supply rail. To realize this in a full system, we first add a software interface for capacitance control from the microcontroller, a small decoupling capacitor to set our initial charge time, and to smooth switching voltage spikes when we toggle the capacitor banks, and finally, diodes to isolate each bank and prevent interbank current that dissipates buffered energy. This is a high-level overview of our unified reconfigurable capacitor architecture that realizes fast charge and high capacity, fully fungible energy storage, and as we'll see later, a transparent software interface to simplify batteryless programming. For a brief explanation of the runtime behavior of React, we start from a cold start with no energy in the system. All capacitor banks are disconnected and energy flows directly from the harvester to the decoupling capacitor, realizing a quick charge time because the capacitor is small. Once that capacitor reaches the upper limit voltage, we connect one capacitor bank in the series configuration to add a small amount of capacitance to the buffer. Once the series mode bank reaches capacity, We can flip the switches to configure it into the parallel mode, dropping its voltage and allowing it to continue harvesting energy from the front end. Once the parallel mode bank reaches capacity, we add more capacitor banks, first in series and then in parallel mode. This allows us to realize arbitrarily high capacity without compromising on charge time, because we only add additional capacitor banks when needed. When we're discharging the system, or reducing capacitance to increase reactivity, we follow the opposite order, switching parallel mode banks into series to boost their output voltage and maximize the energy we extract from each bank, minimizing the energy loss to leakage. We implement and evaluate React on a full hardware implementation shown here on the right, powering an MSP430 FR5994 microcontroller, which is a common testbed for batteryless applications. We build a system using 4 dynamic banks and 1 small decoupling capacitor. We evaluate React on real energy harvesting traces using an energy replay system shown here on the right for repeatable experimentation. We use real solar and RF power traces gathered both by us and other researchers in the community. We evaluate React on a range of reactivity and capacity-bound workloads, sensing, computing, and networking applications that are typical to batteryless systems like this. For baseline systems, we compare it to 3 single capacitor systems spanning the range of capacitance configurations for React, and to similar work called Morphe, with the schematic shown here on the bottom left, which also takes advantage of the charge pump architecture, but in a different way. Morphe uses an entirely interconnected set of capacitors, which allows them to realize a very wide range of capacitance in different capacitance configurations. Unfortunately, the trade-off is that because each capacitor is connected, current flows between capacitors on every reconfiguration event. As we'll see later in the evaluation, the dissipative heating from the current flowing between each capacitor means that Morphe ultimately underperforms static capacitor systems. First high-level takeaway from our evaluation is that React maximizes system on-time. The plot here on the right shows buffer voltage for React and a couple of baseline systems in a typical energy harvesting deployment, with the solid bars on the top showing when each system is actually operating. First takeaway is that React reaches operational voltage on average 8 times faster than an equivalent capacity static system, while also running for ultimately 40% longer than an equally reactive static system, because React never needs to burn off additional input energy as heat. Compared to prior dynamic capacitance approaches, React eliminates the switching dissipation that plagues prior approaches, and brings Morphe's performance ultimately below that of static capacitance systems in realistic deployments. Averaged across all of our energy traces and benchmarks, React ultimately outperforms an equally reactive static system by an average 40%, the next best performing static system by an average 20%, and Morphe by an average 26%, improving performance where the state-of-the-art dynamic capacitance approach actually degrades it. On the design side, React enables an intuitive and easy-to-use programming interface. Shown on the right is our event-driven sense, compute, and transmit model, where it's simple to see that all we need to do is pull how much energy is currently in the React array and compare that to the energy consumption of the upcoming task. Because energy is entirely fungible in React, we don't need to worry about which energy is in which capacitor. Provides a unified, fungible energy interface that simplifies batteryless programming, and ultimately realizes a 54% improvement on benchmarks that have competing reactivity and persistence requirements. In summary, we show first that batteryless systems face competing performance requirements that render static capacitors insufficient. Prior approaches either fragment energy and complicate system design, or face significant energy overheads as a result of equalizing current flow. And we introduce React, which eliminates the charge time capacity trade-off and efficiently combines energy in a unified variable capacitance buffer. The result is an intuitive programming interface and high-performance intermittent execution model decoupled from the power and energy harvesting front end. We open source all of our software and hardware artifacts at the link here below and invite you to read the paper for more details. Thank you.